So in this question, we want to use the properties of logarithms to expand the logarithmic expression. Whenever possible, evaluate the logarithmic expressions. So we're going to be using a set of properties that allow us to expand and condense logarithmic expressions. So I'm going to paste here the different properties that we're going to be looking at for this example. So this example, we want to specifically expand this logarithmic expression, log base 3 of 27 times x squared minus 1. So we're going to be using these properties, the product rule for logarithms, the quotient rule for logarithms, and the power rule for logarithms. So these properties can be used. Their name sort of gives away when you can use them. You use them when you have a product, a quotient, and a power. So when you have a product inside of your logarithm, you're going to make that the log of each factor. And we're adding those together. So you put a log on the first factor, you put a log on the second factor, and you add those logs together. For the quotient rule, you're going to have division inside your log, and you're going to put a log on your numerator and a log on your denominator, just like we see here, but you're going to subtract them. And then we have the power rule for logarithms, and the power rule has inside your logarithm an expression with a power, with an exponent. And you can take that exponent and make it the coefficient of your log. So these are the properties that we're going to use. And when I look inside the logarithm that we have log base 3 of 27 times x squared minus 1. So inside of this logarithm, the x squared minus 1 is an expression that can be simplified a little bit more. X squared minus 1 is called a difference of squares. So we could actually factor that a little bit more. You can write that as log base 3 of 27 times x plus 1 times x minus 1. And the reason I did that is because that produces an extra factor for us. We have 3 factors. We have a factor of 27, a factor of x plus 1, and a factor of x minus 1. And so when we use the product rule, this example I've given you only has 2 factors, and we're going to use 3. So that can be written as log base 3 of 27 plus log base 3 of x plus 1 plus log base 3 of x minus 1. So you'll notice that I kept the base of 3 on all of them, and we used addition because we are using the product rule. Inside of the log, we had a product of all of those factors. And the last thing that I'm going to do is to simplify this right here. The other 2 have a variable in it, and so we can't do any more simplification on those terms. But this term that is log of a number, I'm going to be able to simplify. So on the side over here, we're going to figure out what log base 3 of 27 is. So log base 3 of 27 is some power. I can rewrite that as an exponential. That's 3 to what power is 27. 3 to the third power is 27. And so this logarithmic expression, log base 3 of 27, is equal to 3. So we can write that as 3 plus log base 3 of x plus 1 plus log base 3 of x minus 1. For this question, we want to solve the exponential equation using the method of relating the bases. First, by rewriting the equation in the form b to the u equals b to the v. So relating the bases involves us writing the equation in this format, b to the u equals b to the v, and this relating the bases property says that we can simplify to having the exponent on the left equal the exponent on the right. So this example is 2 to the x equals 8. And on the right-hand side, I can rewrite 8 as 2 cubed. And we have 2 to the x on the left. And now we've written it so that we have the same base on both sides, just like we have here. And so these exponents must be equal to each other. X must equal 3. And that is the solution to this equation. In this question, we want to solve the exponential equation using the method of relating the bases by first rewriting the equation in the form b to the u equals b to the v. We want to write it so that the bases are the same, and then when we do that, we're going to be able to use this property of relating the bases that says that the exponents must be equal to each other. So we can see on our example, we have 6 to the x squared over 36 to the x equals 216. So right now we don't have the bases being the same on both sides. So we need to do that first. So I have a base of 6 here, and then I notice 36 is 6 squared, and 216 is 6 cubed. So we're going to be able to write all of these expressions with a base of 6. We have 6 to the x squared over 6 squared to the x equals 6 cubed. And on this portion of the expression, we have 6 squared, an expression with an exponent that is then raised to a power. So there we can use the power rule for exponents. And with the power rule for exponents, we multiply those powers together to get 6 to the 2x. We're getting close to having the same base on both sides, and now you'll notice that we have the same base being divided. So there we'll use a property called the quotient rule, and the quotient rule for exponents allows us to subtract the exponents. That's going to be a base of 6 with x squared minus 2x on the left-hand side. When you have the bases being the same, we're allowed to say that the exponents are equal to each other. So we're now at the step where we can simplify this equation by setting the exponents equal to each other. This gives x squared minus 2x equals 3. I can move all the terms to the same side and solve this quadratic equation by factoring. It gives x and x, 3 and 1, minus on the 3, plus on the 1. We're going to set each factor equal to 0, and that gives x equals 3 and x equals negative 1. These will be the solutions to the equation, x equals 3 and x equals negative 1. On this question, we want to solve the exponential equation. And our equation is 9 to the x over 2 equals 20. So up on the top I have a table of different methods for solving exponential equations. And the first method that is sort of our go-to method is called relating the bases, or uses what's called the one-to-one property for exponents. And in this method, you try to make the bases the same on both sides, so that you can use that one-to-one property and say that the exponents are equal to each other. And if you look at the bases in our example, we have a base 9, and 9 is the same thing as 3 squared, so you could change that to a 3, but 20 is not an exponential expression and can't be changed to 1. I guess technically it can be written as 20 to the first power, but we can't change that base to some other base easily. So this method of relating the bases cannot be used in this example. However, we have these other methods that are available to us for solving. We could try to convert to an exponential, or we could try to take the log of both sides. I'm going to show you both methods. When you convert the exponential to a logarithmic equation, you're going to use the definition of a logarithm, and you follow this pattern that you see here. If you start with y equals b to the x, you would write that as a log equation, log base b of y equals x. The other method is to take the log of both sides. This is something that we're allowed to do because logarithms are one-to-one. And so you would start off with y equals b to the x, take the log of both sides. Then you can use properties of logarithms. You're going to use the power rule for logarithms on this step, and then you're going to solve for your variable by dividing. So let me start by showing you the first method. So if you would like to convert to a logarithmic equation, this is the way you would do it. You would use log with base b, that's base 9. The log always equals the exponent, so the exponent is x over 2. And then what's inside the log is going to be what our exponential expression equals, so 20 goes here. So that gives log base 9 of 20 equals x over 2. Then we need to solve for x, so we would multiply by 2 on both sides, and that gives x equals 2 log base 9 of 20. So that's solving it with the method of converting to a logarithm. Now the other method is to take the log of both sides. So we would start with our original equation, 9 to the x over 2 equals 20. We take the natural log of both sides, that's natural log of 9 to the x over 2 equals natural log of 20. We're going to use the power rule for logarithms, which allows us to move that power into the coefficient. So that's x over 2, natural log 9 equals natural log 20. And then I can solve this by getting x by itself. So to get that x by itself, I've got to get rid of this 2, which is divided, and this natural log of 9, which is multiplied. So what I can do is I can multiply by the reciprocal. I can multiply by 2 over natural log of 9, and that will cancel out the 2's, and that will cancel out the natural log of 9, leaving me with x, and that gives 2 natural log of 20 over natural log of 9. Now when you look at these two answers, it doesn't look like they're the same. But if we type both of these into our calculator, you'll see that they come out to be the same decimal. So let's take a moment to type them both into the calculator and confirm that they're actually the same value. So I've got my calculator here, and I'm going to type the log on the left in. Let me clear this out so it doesn't look quite so messy. And I can use, in the math menu, at the bottom, there's log base. And I want to do log base 9 of 20. Whoops. Log base 9 of 20. And I really should have multiplied by 2 first, but I can multiply by 2 right now. And that's approximately, let's say, 2.73. If we round to the hundredths place. And then let's type in our other log. We're going to put parentheses around our numerator. 2 natural log of 20. Close parenthesis for the log, close parenthesis for the numerator. And then we're going to divide by natural log of 9. And close parenthesis for the log. And we get approximately 2.73, just like the other one. So even though the answer we get on each one of these looks a little bit different, they're just an equivalent way to write the answer. For this question, we want to solve the exponential equation. 1.73 to the x equals square root of 3 to the 1 minus 4x power. Up top here, I have a table of different methods that we could use for this problem. The first one is called relating the bases, and we want to try to make the bases the same. And this one can be a little bit tricky. I'm going to pull up my calculator here for a second because I want to show you something. I'm not sure if this question is meant to trick you, but if you were to calculate the square root of 3, you get something that is pretty close to 1.73, which is the base on the other side. But they're not exactly the same. So this, even though they're close, you can only use that relating the bases property when the bases are exactly the same. So we're going to skip that method of relating the bases for this example because those bases are not the same. So we're going to use one of these other methods. And the two methods are that we could convert the equation to a logarithmic equation, or we could take the log of both sides. Either one will work. I usually prefer to do this method here where you take the log of both sides. And the reason I like that method a little bit better is because it makes it easier to type in my calculator. So I'm going to pull up the calculator for a second and explain why. So on the home screen of the calculator, I have a button for natural log. And with that method of taking the log of both sides, as long as I use, you don't have to use natural log. You could also use log base 10 or honestly any base you want. But I always use natural log because the symbols are special and that button is on the home screen of my calculator. If you were going to use this method of converting your log would have the base that is in your exponential. So it would have this space or it would have this space. And in this calculator, that button is not on the home screen. You have to go into the menu, the math menu, and down here at the bottom of the list, you have a log where you can specify the base. So I'm choosing to do this method of taking the log of both sides so that when I get my answer, it's a little bit easier to type in my calculator to get the approximate value of the solution. So let's take a look. And let's start by rewriting the question. We have 1.73 to the x equals square root of 3 to the 1 minus 4x power. And the first step is that I'm going to take the natural log of both sides. And once you introduce the log, you have log properties that are available. And the one that we're going to use is called the power rule. The power rule for logarithms allows us to take that exponent and move it to the coefficient of the log. So that will give x natural log of 1.73 equals 1 minus 4x times natural log square root 3. Next, I'm going to use the distributive property, and I'm doing that so that I can get rid of these parentheses. And I'll use that distributive property and multiply natural log square root of 3 to both terms in the parentheses. And that will give x natural log of 1.73 equals natural log square root of 3 minus 4x natural log square root of 3. The next thing I want to do is to try to solve for x. I've got x in two terms. I want to move those terms to the same side of the equation, so I'll move that over here so that the x's are on the same side. That gives x natural log of 1.73 plus 4x natural log square root of 3 equals natural log square root of 3. Now that I have the x's on the same side, I can factor out the x. That's x times natural log of 1.73 plus 4 natural log square root 3 equals natural log square root 3. And now I'm able to isolate x by dividing both sides by natural log of 1.73 plus 4 natural log square root 3. So this is going to give x equals natural log square root of 3 over natural log 1.73 plus 4 natural log square root 3. So I have my solution. This is called the exact value of the solution, and it's exact because you're not rounding at all. When I type this into my calculator, it's going to give me the approximate solution, and the approximate solution is going to be rounded, and it's going to have a little bit of error because we rounded, and that's why we don't call that one exact. So let's type this expression into our calculator. Let me clear this out so you can see the buttons that I'm typing. So in the calculator, we want to type natural log of square root 3. I'm going to close parenthesis for the log and then divide. And I need parentheses around my whole denominator to make sure we're dividing by both of those terms and not just the first one that we typed. It's going to be natural log of 1.73 3 plus 4 natural log square root 3. So I hope you can see why I chose that other method. You don't have to, but we used natural log 3 times in this, typing this, and that would be a lot of times that we would have to go hunt into the menu to find that other log function. So we have got that this is approximately 0.40 if we round to the hundredths place. For this question, we want to solve the exponential equation 72e to the x minus 2 equals 3. So up here in the table, I have some different methods that we could use to solve this equation. We're not going to use relating the bases because we have a base of e and numbers that are not e on the other side. So we're not going to be able to use this relating the bases method. But we could use these other methods of converting to a logarithmic equation or taking the log of both sides. Let me see if I can show you both methods. One thing I want to point out to you guys is that when you use these methods, what you'll notice is that you have an exponential expression that is isolated on one side of the equation. And in order to use them, we must do that first. And so in our example, the exponential portion is the e to the x minus 2. This is the exponential portion. So I'm not able to use the methods that we see above until we've isolated that portion. So we want to divide by 72 on both sides. That's going to give e to the x minus 2 equals 3 over 72, and I can reduce that fraction. 3 goes into 3 once, and 3 goes into 72. Let's see, 24 times. So once we get to this point, let's talk about how you would do this problem with the method of converting. If you were going to convert this to a log, you would use a base of e. You would use x minus 2 as what the log equals. X minus 2 is the exponent. And 1 over 24 goes inside of the log. And so when we convert, just on a side note, we don't typically write base e. We have special symbols for that. We're going to write natural log of 1 over 24 equals x minus 2. Now that we've converted, we're going to solve for x by adding 2 to both sides. So we get our solution being x equals 2 plus natural log of 1 over 24. But what if instead of converting, we wanted to use the other method of taking the log of both sides? So if we use that method, we're going to start off with e to the x minus 2 equals 1 over 24. We're going to take the natural log of both sides. And then there's a property of logarithms called the power rule that allows us to take that exponent and move it into the coefficient. That's x minus 2 times natural log e equals natural log of 1 over 24. We can simplify natural log of e. That is equal to 1. 1 times x minus 2 is x minus 2. And then we want to solve for x, so we're going to add 2 to both sides. and get x equals 2 plus natural log of 1 over 24. And you can see with this example, we got the exact same answer using both methods. Thank you for checking out my videos. Have a great day.